Hello everyone, and welcome back to Advent of Code. We're going to be doing day 5 here. Let's get started. Alchemical reduction. You've managed to sneak into the prototype suit manufacturing lab. Why into instead of into? No note about this like there was for sneaked last episode, but okay. The elves are making decent progress, but are still struggling with the suit's size reduction capabilities. While the very latest in 1518 alchemical technology might have solved their problem eventually, you can do better. You scan the chemical composition of the suit's material and discover that it is formed by extremely long polymers, one of which is available as your puzzle input. The polymer is formed by smaller units which, when triggered, react with each other such that the two adjacent units of the same type and opposite polarity are destroyed. Units' types are represented by letters. Units' polarity is represented by capitalization. So we're looking for adjacent units of the same type and opposite polarity, okay? So touching letters that are different case. Okay. For example, yep. So are we just reducing this until it goes away, or what? After all possible reductions, how many? Yeah. Okay, so we're just given an input and a transition function that may or may not change the input, and we are asked to keep transitioning it until it no longer changes. Now, the case that was not addressed here is what about lowercase a, capital A, lowercase a, all adjacent to each other? Do those all three get disappeared at once? Or does it not? Ah, it's covered here. So they only react in pairs. And whichever pair you happen to remove, it doesn't matter, right? Like, we can remove this and leave a lowercase c. Or we can remove this and leave a different lowercase c in the same place. Okay, fine. Well, this seems quite easy, isn't it? Yeah. I mean, I've said that in the past and spent an hour and a half on camera, but hopefully not today. So let's grab our input here. Fine. It's long, it's letters. That's about what we expected. Oh, whoops, I'm in the library folder of this thing, which I don't really care about. So good news, we won't need any parsers. Honestly, parse is just identity, so let's like delete this whole junk. I mean, we could parse it into like an object, which has a type and an is same case or whatever, but like I'll just define a reacts with function that takes two objects and tells you whether they react with each other. So in fact, I think that like pretty much everything you want to do in this is we want basically like a couple of functions. We want reacts with takes two characters and returns a bool, right? And reacts with, how does Haskell character uppercase, how do you do that? Okay, in data.char, there are functions called toUpper and toLower. So let's grab those. Do I need both? What exactly am I going to do here? I mean, A and B react to each other if A is not equal to B and A equals toUpper of B, or B don't want that here. I want it here. Or b equals 2 upper of a, right? For example, let's just test this real quick. Oh, capital U. And input is just going to be a string here. Is our input file a single line, by the way? I assume so. Yeah. What's the right way to check that? Yeah, 1 line. Cool. But it's got a new line at the end, the way I pasted it, so I will need to be a little careful. Right? I'm just looking at the here. It's letters, yeah. And I bet if we looked at the actual input file, it would not have a new line at the end. I'm not sure though. Maybe it would. So, do I have an is letter in data char maybe? Is letter? Yes. Cool. So instead of like chopping off the final new line at the end, I'll just filter for letters. It'll have the same effect. But worked better in case someone gave us something that didn't end with a new line. Now we're ambivalent to whether that is the case. And the next thing is to say like, let's write next is a function from input to input, I guess. No. Either input or input. So in a way, this is just the same as a Boolean and an input, but I plan to use some monadic machinery with it here, and this is a convenient type to have. So basically, like, I want next to look at a string, and if it finds a single change to make, it should make that change and return right the new string. And if it finds no change to make, it should return left the original string. That will be somewhat convenient because of the type of forever when applied to ethers. And in fact, let me show you. Next equals undefined. So suppose... what is the type of forever? It's in data.monad, that's what it is. Control.monad, I mean. Oh, it's in applicative now. I guess that makes sense. Or it's in control monad, but it only requires applicative. Sure. So forever is a weird one. It's basically like writing an infinite loop, but in between each step, you use monadic bind. And because the bind for ithers doesn't call the function if... I mean, let me just double check here. Like, what is forever of left 1? It's just left 1, yeah. Whereas if I say forever of right 1, it'll, like, never finish. Fine, that's what I expected. So my idea is to... Oh, I don't want forever, do I? Because forever doesn't take a function. What is there that takes a function that like binds the same function over and over? Like, is there an iterate m? No. How about mfix? Fix m. All right, let's look on Google. I'm looking for a function which takes an monad m, takes an MA and a function from A to MB, and returns an M of A. Yes, there's all the binds and things, for M, catch, map M, filter M. None of these are what I want. Like, what types are there, functions are there that have the name fix in them? Like, or iterate M? Mfix? Like, that's a thing. Monad fix. Oh, that's a little fancier than what I need, huh? Would not, in fact, be what I want. Okay, well, fine, I guess. We'll just have to do it differently. I don't get it. This seems like the kind of thing that Forever should be able to do. I mean, we can do it. Like, we could define bind forever to be a function with the type that I specified, an MA and a function from A to MA that returns an MA, and bind forever of what order should I take these in? I guess actually this is sort of a more natural ordering. Bind forever fx is equal to let, like, I can use fix here, right? Oh, fix bind f? Is that close? Where the hell does fix come from? I assumed it was in base. I guess not. Is it in like data function or something? God, get me back to Hoogle, please. Hoogle. Where's not Dix? Fix, please. Data function. Yeah. Okay. Well, the more you know. Dat function. Yeah. Well, maybe I shouldn't be so fancy. Let's just write it. F of x equals f bind, or x bind f. Wait, did I just have it? No, that was right. X bind to f. And bind that forever with f. So why wasn't that the same as this fix? So, like, okay, I've written this function now, and what I have in mind is that, like, if I say bind forever with a function that is, well, let's let f of 5 be nothing and f of x equal just of x plus 1, for example, right? And we can say f of 1 is like just 2, f of 5 is like nothing. So what I hope is that bind forever with f on 1 will eventually give me back nothing. Or it'll give me, yeah, as a maybe int, please. Why? Oh, I had to say just one. It doesn't return anything. Why? Ah, because we're calling bind forever. Okay. We're calling bind forever unconditionally. What we need to do is call it inside of the scope of the bind function. So we need x I don't know. I mean, we want to bind it to f and then do something to the result, right? Which really is going to be the same as, well, I don't know. I can just say, now I have this value. Like, this bind has succeeded. And I want to take the result and, assuming it bound to something, bind it to, what is a function? Well, okay, would you help me out here? Like, what is the type of this thing that I need to write, please? A to MA. And it needs to involve bind forever somehow. I don't know. Man, I thought this was going to be super easy. Just use forever and like... I want to find like... I have a function and I'm looking for like the attractive fixed point of that function, right? Attractive fixed point in Haskell. So I have fix, but I'm not. I can't be that general. I need to look for the attractive one or attracting or something, right? Attractive fixed points. So, oh no, that's not what I want at all. All right. I mean, this is a lot of work to just avoid having to check whether the input to the function is the same as the output, right? Like putting in this like crazy... I just thought it would be really easy to just like convert it to a left or a right and then use existing machinery. But actually, apparently that machinery is not so easy to use. And so like, why don't... I'll just write a function from input to input that might return the same value, and then I'll have something else iterating that checks whether it was the same. I still feel like there's a cleaner way to do this, but okay. Next of... Do I need to check empty? I don't, right? So if there's only one item in the... Oh, actually, what I should do is x as nothing equals x. So if the list has a single element, I don't care what it is, just return the original list. Well... But like if I'm doing it... I don't know. Next of x, y, x's, if x reacts with y equals x's. Is that correct? Yes, we just remove x and y. And otherwise equals x cons to next of y x's. for example, we can now write next of A, B, B, C, and we get AC. So that's all lovely. And I guess we can write collapse input to input. Collapse of S is let S prime equal next S. This autocomplete, man. Well, no, I don't need to do a let in. I can use a where, and then it'll be much nicer. Such that, so if S is equal to S prime, then it is equal to S prime. Otherwise is equal to collapse of S prime, where S prime is next of S. So we haven't used a where clause like this spanning multiple guards before, I don't think. But in fact, you can do this. A where clause that you define spans a single pattern, where here the pattern is just S, across all of that pattern's guards. So here there are two. So we're saying, basically, before we do any of this stuff, we define S prime to be next S. And then we say, okay, well, was it the same as S? I guess I'll return the input. Why not? And otherwise, we'll just collapse it again. So part one is pretty simple, right? It's just, I need to know how many are left. So it's just length collapse. Like, that's it. Let's see what happens. It's a bit slow. I didn't think it would be this slow. I guess, to be fair, it is 500,000 items, and we're not iterating over the list in any smart way, right? As soon as we find a single item, we abandon that iteration. Okay, we can do better than this. This is, I think, in principle correct, but doesn't... we can just say next of x's here, right? We removed two things. Now let's keep going and remove as much more as we can before reconstructing the list. And that should reduce the amount of, should greatly reduce the amount of walking over already known items that we do. Why can't I, like, I have a, isn't there usually some text under this bar here? Maybe not. Okay, 9562. So that did speed things up quite a bit. How many units remain after reacting? Great, we did it. Time to improve the polymer. One of the unit types is causing problems. It's preventing the polymer from collapsing as much as it should. Your goal is to figure out which unit type is causing the most problems. Remove all instances of it, regardless of polarity, fully react the remaining polymer, and measure its length. Interesting. So we basically just want to... I don't think there's any way to be clever about this. Is there? So I guess there is. So first note that we could simply like look through the input for all of the letters that it contains before doing any reducing. And then for each one of them, remove them all from the string and try a reduce. That would be fine. It would work, but we'd be repeating a lot of work. What we can do instead is first fully reduce the polymer as much as we can. Yeah, and that's guaranteed not to ruin anything. And then, for all the items that are left, try removing each of them. And then fully reduce again from there. So that should certainly be faster. And what is the length of the shortest polymer you can produce by removing all of exactly one? Okay, well, let's start by day 5, part 1. So our next and collapse functions are all still very useful. We just need to do something a bit fancier in part 2. So let's say part 2 of S is let. We'll probably want some lets here. Reduced would be collapse of S. And then, what do they call these? Units? Units equals map to upper of reduced. These are all the things we could consider removing. And then I guess we want in maximum, which is in data list, right? Yeah. Import data list maximum map, no, minimum map length of do. So now we're going to iterate over unit, each unit in units. And return what? Well, maybe this is a little simple, too simple for a list comprehension, but fine, whatever. Or for do notation. Pure of collapse of remove elem of unit and to lower of unit reduced. Oh, remove doesn't exist. I'm used to Clojure where we have filter and we also have remove, which is just like takes the opposite. And I just never get the hang of having filter but not remove. Filter of not this. Okay. I mean, it compiles. And it should take a little while, but not much longer. So I guess while we're waiting on this, let me explain this a little more carefully. So we collapsed the input, and then for each item in the result, we took it to uppercase. Oh my god, this is going to take forever. I missed a very important step. We did not uniqueify, so we were actually iterating over every character in the string, not every unique character in the string. Okay, try again. Right, so for every... we looked at the uppercase version of every character remaining in the string after reducing it. And then we're going... This do notation here constructs a list of all the ways you could remove one letter from the string, or one kind of letter from the string. then collapse it. So once we've constructed that list, and I'll get a little bit more into how it's constructed, we want to get the length of each of those and find the minimum of those possibilities. So looks like it's done. Let's see if we got the right answer. Great. Okay. So back to explaining. So we do this do notation where we say choose a unit from units. And then this is a bit long, but we have a list of operations we want to perform in order on reduced. And that's what all these function compositions are for. It's a very nice, common Haskell style to, where possible, try to do things as function composition rather than, you can do that here too, right? Like I could have just said, and in fact, it might be nicer. But okay, let's commit what I have. Day 5, part 2. And then we can play around with some alternatives. All of this really could be one big function composition applied on S or on reduced. We could say, well, we kind of need reduced twice, right? Like, so it's useful. Notice that, like, there are two other places where reduced appears, right? And so it's a bit less convenient to write things as a function composition if you need to reuse a value. It's not impossible by any means, like, but it's often simpler to let bind stuff if you want to refer to it twice, and then you have a name and you can refer to it as many times as you want. So we might do this, but notice that, like, well, actually, how easy is it to collapse any of this stuff together? We can't, like, I was thinking at first of collapsing, like, of basically writing something like this, which is, it gets rid of that binding, but we need that binding down here. So that's not so great. And I was also thinking, like, well, okay, we kind of have, like, a list of functions we're calling on reduced. Well, I was thinking, well, can't I just write some more list comprehensions here? Some of the stuff, there's some more compositions. Some of the stuff here, couldn't I lift it to outside the do? And that's actually not so easy. Because these function compositions are not applied to the same thing, right? This is I've built a single function which is called many times, once for each unit in units. And so you don't want to just filter it in here. One point is we could say, we could put the length down here, and that would probably be more reasonable. But I don't know, like, yeah, minimum of do, fine, but it's kind of nice, even though it introduces this extra map, like, there's one extra token in the input, right? But it kind of conveniently, it's more expressive, I think. It says, here, we want to find the minimum length of a bunch of things. And so you can sort of keep in mind as you're reading the rest of it, like, okay, this is going to be returning a number, and we care about its length. If you instead see this, you're like, okay, well, it can be the minimum of something, and, like, these will be numbers. What do the numbers mean? It's not totally clear. And you have to scan down to here, and it's like, oh, it's the length of collapsing, of filtering. I don't know. I kind of like the original version better, to be honest. Anyway, so we choose a unit from units, and then we try removing that unit from the polymer and see what happens. So we take reduced, the already reduced polymer, and first we filter it, removing or keeping only items which are not an element of the set unit to lower unit. So either the uppercase or lowercase version. Having done so, we just collapse it again and return. And say, here's the candidate. What do you think of it? And the minimum in the map length up here decides what to do with it. Cool. So all in all, pretty simple. And shorter than any of the recent ones have been. I spent most of my time, in fact, looking for a function that doesn't exist. I still feel like there ought to be some way to write that function that I wanted. Right? Like, because don't I just want like fix of bind f? Like, why wasn't that correct? Let's say I wrote react prime is a function from next prime, right? Because that's the level we were working on. Next prime is a function from input to either input. That's the type we wanted. And I can say next of, like, basically this, right? I can just copy all this, but, whoops, produce a different thing. Is right, no, it's left of x. There was nothing to reduce. Wait. Oh, well, okay. So the problem is now I can't clearly say whether we succeeded in reducing because we do multiple reductions in one step. But let's go back to the naive version and just don't call next here. And we'll say write x's. Okay. So if we get to the end and found nothing to react with, we return left and say I'm done. If we reacted with something, we remove those things and say write, yes, I found something, you can keep going. And otherwise, we just we map the action of consing x onto the front into the result of the recursive call calling next on y cons to x's. And you can see that like should work fine. Next prime of a, well, let's just next prime. It says, yeah, write AC. And if we then say to that, bind next prime, it'll say left C. Oh, that's not right. Yeah. That's just the characters that are left when you got to the end. Uh-huh. Yeah, very funny. Okay, well, it wouldn't have even worked very well for this next prime that I had in mind, apparently. But I still don't understand why that function that I wrote before doesn't work. So let's go back to this. We defined f, right? And it's this function. And I'll even be like, I'll say left of done, and otherwise right of this, okay? And I want to just bind f to a value forever until we get a left. Well, and even bind after that, but all those binds won't matter. So, okay, maybe it'll be simpler to write with do notation. So suppose I wanted to write bind forever again of takes a monad M and an A to MA and an MA and it returns a different MA, right? And I kind of want bind forever of F and X to be do X prime should be the result of calling Well, let's call this mx because it is wrapped in a monad at the moment. And we'll say x come from mx, please. Then call x prime be f of x. Now we have a value of the right type to keep going, and so I can just say bind forever. Wait, I don't want to unbind it, do I? I just want to say bind forever with f of fx, right? This type is correct. Does it ever, like... Does it do something? Well, I guess it's bind forever f and just right one. Yeah, we get left done. Okay. So my thinking was that we would have a function which takes an input string, polymer, right, and tries to reduce it. If it succeeds, it returns right of the thing. If it fails, it returns left of the thing. And then we could just use this bind forever to say keep going until you get to a point where it declares itself to be finished. And we would look at the value in the left. And that would be our answer. It turns out it wouldn't have actually worked very well because next can't really return the whole string. In the case where it failed, because I mean you could, but it kind of sucks. Because the fmap only applies over the stuff in the right. It wouldn't apply over the thing in left, and you'd have to do that by hand, and like that really stinks. You'd basically just like be working with a pair of bool and x and like pretending it's in either, and that kind of sucks. But okay, we have this function, and it's actually kind of cool. Like, I guess if all you guys care about is advent of code, like, thanks for watching, and I'll see you next time. But I want to explain, like, why does this function even work? It looks impossible, right? It always, it looks like, calls bind forever itself recursively. And that doesn't seem like it should work. But it's kind of a... What's the type of fix, right? Oh, did I import that? I did. Oh, well. So fix is like... If you look at the type signature, and you haven't seen fix before, go ahead and, like, take a minute to pause the video and ask yourself, like, A, what does this type signature mean? B, how could you possibly implement a thing with this type signature? Okay, so if you went and did that exercise, welcome back. This type signature basically means if I just give you a function that takes a value of type A and produces a different value of type A, but don't give you any values of type A to call the function with, you can somehow materialize a value of type A just from the function itself, without knowing anything about what the type of A is. And this just seems like baffling. It could never possibly work, right? And indeed, for many types, or anyway, many functions, it doesn't work. So fix is not a function that is guaranteed to return if you give it a function which is not compatible. But there are, in fact, many functions where it can return. For example, let's write take 10 of fix 1 cons. So this is the function which conses 1 onto some value, adds 1 to the front of a list. And when you fix that function, you get an infinite list of 1s. Which, like, that's bizarre. How does it happen? It's because of laziness, right? So fix f and x, I won't show, this isn't the real definition of fix, but it's equivalent, is equal to fix with f, I think. No. Fix f equals, actually you kind of have to do it the real way, don't you? Let x equal f of x in x. So we're defining x circularly in terms of itself and then returning that value. And this only works because of laziness. I've now redefined fix, and we'll see that my version works just as well as the one in the standard library. And if you expand this a little bit, let's say we can make the fix of 1 cons equals let x equal 1 const x in x. And because of laziness, x, this function, when you call it, it doesn't need to look at its argument in order to produce something. It can produce a list starting with 1, followed by like a thunk that when you evaluate it will maybe do something. We'll compute the rest of the list. And what that means is x is like 1 const onto the list x. And in that way, you can sort of like just sort of follow that circular pointer back to the same value over and over, seeing, well, there's a 1 followed by something. What's it followed by? A 1 followed by something. What's that followed by? A 1 followed by something, and so on. And bind forever uses the same sort of trick. I'm pretty sure we could have written this as a fix, and like, obviously we could, right? In fact, let's first just say mx bound to, and we'll just desugar this manually and then figure out how to simplify it. Bind forever fx, right? This is equivalent. This is what the do notation desugars into. Which I guess is equal to mx. Why do I keep typing those backwards today? Bind forever f composed with f. I don't understand why that solution is correct at all, but it is. What the fuck does that mean? Huh. So you call f. No. Because it's actually parenthesized like this. We bind to a function which first calls f and then binds the result forever with f. I guess that makes sense. Huh. Anyway, and so the magic is that we basically insert an unlimited... This is... Well, actually, we can simplify more and write this. It's that. And if we want to reduce this f out, it's pretty awkward, but... This is basically calling, you know, x bind to something, bind to something, bind to something, bind to something, bind to something forever. The trick is that the bind for ethers, if the input is a left, it doesn't call the function. Or it doesn't even look at the function that's being bound to it. It just returns the left value right away. And so since the function being bound to it is one that involves one of those binds, you know, it doesn't get called, and we just return the left value. So it's kind of cute. And I thought it might have helped, but actually it doesn't. And hopefully it was an interesting exercise for you guys to like look at and think about it a bit. But I guess we're done for today. So that's it. Thanks for watching, and I'll see you next time.